Hi everyone, welcome to Engineering Mechanics, and for this video we will talk about the resultant of force systems. For part A, we will be dealing with two-dimensional force systems, and to start with, let us first define what is a force. So a force is an action of one body on another, then it is a vector quantity. When we say vector, it has both magnitude and direction. Then it can also be external and internal. So we have concurrent forces. So in this force, the line of action intersect at a point. So the figure on the left shows that F1 and F2 are concurrent forces because if we extend the line of action, they meet at point A. So therefore, we can call them concurrent forces. So vector components. So a vector can be resolved into several vector components. Then the vector sum of the components must equal to the original vector. For rectangular components, we have here in an example of force F, which can be split into its rectangular components F sub x and F sub y. Then the magnitude of F sub x can be obtained by this formula F times cosine of theta, and the magnitude of Fy can be obtained by the formula F sine of theta. So Fx is basically the component of force F along x-axis, and the F sub y is the component of F along y-axis. And to get the angle theta, we have angle theta is equal to arctan F sub y over F sub x, and the magnitude of force F with respect to its horizontal and vertical components, we have force F is equal to the square root of F sub x squared plus F sub y squared. Then the rectangular components are convenient for finding the sum of the resultant R of two or more forces which are concurrent. So for this example, we have F1 and F2 force. Then to get the resultant R, it is convenient to obtain first the rectangular components of F1 and F2 and combining them, and uh, in order to get the resultant vector R. So for actual problems, it do not come with reference axis. So you can choose the most convenient one for you. So we have here the example number 1. So the link is subjected to two forces F sub 1 and F sub 2. So we are asked to determine the magnitude and direction of the resultant force. So to get the magnitude and direction, we first get the x component and y component of each forces. So for F1, we have for F1, the x component is F1x, which is equivalent to F cosine of theta. So we have for F1, we have 600 Newton, and the angle is 30 degrees. So cosine of 30 degrees. So the result is equal to 519.6 Newton. Then the y component, we have F1y is equal to F1 sine of theta 1, which is equivalent to 600 Newton sine of 30 degrees. So equals 300 Newton. Then for force number 2, we have F2x is equal to 400 cosine of 45. So we have 400 cosine of 45, which is equivalent to 282.8 Newton. Then F2y is also equal to 400 sine of 45, which is also equal to 282.8 Newton. Then taking the summation of the forces, we have Rx is equal to the summation of forces along x-axis and taking the direction towards the right as the positive direction. So we have for F1, we have 519.6 Newton. Since it is directed towards the positive, it is positive. Then F2, since it is directed towards the negative x-axis, it should be negative. So for F2, we have minus 282.8 Newton. Then Ry equals the summation of forces along y-axis, then taking the upward direction as positive. So we have 300 Newton plus 282.8 Newton. So our Rx is equal to our Rx is equal to 236.8 Newton, and our Ry is equal to 582.8 Newton. Now, if we draw the resultant vector, we have from the origin, this is R, and this is Rx since it is positive. Then this is Ry. So to get the magnitude of R, we have R is equivalent to the square root of the square of Rx plus the square of Ry. So we have square root of 236.8 squared plus 582.8 squared. So it is equivalent to 629 Newton. Then for the angle, we have uh, theta is equal to arctan ry over rx. So equals arctan. So our ry is equal to 582.8 and our rx is equal to 236.8. So our theta is equal to 67.9 degrees. So this angle theta is equal to 67.9 degrees with the x-axis. And that's our answer for example number 1. So for coursework number 1, you need to determine the x and y scalar components of each of the three forces. Then you need to write this in a long size bond paper together with the given drawing or diagram. Then submit it on the next meeting. So the rectangular components of a unit vector, say for example we have a vector v. So the unit vector is represented by vector v divided by the magnitude of the vector. So vector b can be split into its components. We have vxi plus vyj. So divided by the magnitude of the vector b. So we have here cosine of theta x and cosine of theta y, and these are called direction cosines. So in example number 2, we have the line of action of a 34 kilonewton force runs through a point A and B as shown in the figure. So we are asked to determine the x and y scalar components of our force F. Then write the force F in vector form. So for letter A, we have we need to get the coordinates. So the coordinates of A is equal to -7 and -2, while the coordinates of B is equal to 8 and 6. So if we draw a line from A to B, we can form a triangle like this. Then this length is equivalent to our y2 minus y1. Then this length is equivalent to x2 minus x1. So we have for y2 minus y1, we have our b is 6 minus -2, so we have 8. Then for x2 minus x1, we have x2 8 minus -7, so that is equivalent to 15. Now, to determine the x and y scalar component of f, we have, so let y2 minus y1 equals y. Then x2 minus x1 equals x. Then the length AB should be, let the length AB be equal to our D. So our D is equal to the square root of x squared plus y squared. So it is equal to the square root of 15 squared plus 8 squared. So equals 17. So in order to determine the scalar component of force F, so in the next slide, since our x is equal to 15, our y is equal to 8, then our D is equal to 17. So our fx is equal to f cosine of theta. And from the triangle, if this is our angle theta, we have here our x and our y, and this is D. So cosine of theta is equal to x over D. So for fx, we have f, which is 34, times our x is 15 divided by 17. So we have an fx, or the x component of our force F, which is 30 kilonewton. So for our y component, so we have Fy is equal to F sine of theta. Then it is equivalent to F times y over D. So equals 34 kilonewton times 8 over 17. So which is equivalent to 16 kilonewton. Then to write the force F in vector form, so we have the vector form of F is equal to Fxi plus Fyj. So we have an Fx of 30 kilonewton. So 30 I plus our Fy of 16 kilonewton, 16J, then the unit is kilonewton. So this is our answer for B. Then this is our answer for A. So we have a moment. So in addition to tendency to move a body in the direction of its application, a force also tends to rotate a body about an axis. So the axis is any line which neither intersects nor is parallel to the line of action. Then the rotational tendency is known as the moment m of a force. Then to get the moment, it is just equivalent to the force. So we have force F multiplied by the perpendicular distance from the axis to the line of action of the force. So the moment is a vector m perpendicular to the plane of a body. So it is also a directional since it can be in a clockwise or counterclockwise direction. Then a vector approach for the moment calculations is proper for 3D problems. So the moment of f about point A may be represented by a cross product. So we have the cross product of r times the force F, and it is equivalent to FR sine of theta. So in example number 3, calculate the magnitude of the moment about the base O of a 600 Newton force. So in order to get the moment of this example, we need to determine the R. So since M is equal to F R sine of theta, so we need to get the value of R. So in this example, if we extend the axis of the force, so from this point up to this point O, we can say that this is the R and this one is the angle of theta. Now, for the drawing to be clear, let us draw the diagram. So this is 600 Newton and this is our point O. So this is our theta. This is 40 degrees and this is 4 meters. This is 2 meters. So let this length be equal to our y. Then our r is equal to y plus 4. So since we have an angle of 40 degrees, we can say that this angle also is equal to 40 degrees. And we can get the value of y by the expression y is equal to 2 tan of 40. So substituting the value of y into this equation, so we can get r is equal to 2 tan of 40 plus 4, which is equal to 5.68 meter. Then substituting the value of r in the equation, so we have the moment m is equal to the force F, which is 600 Newton, times our r, which is 5.68 meter, times sine of theta. So our theta, based on the figure, so this is our theta, and this is 40 degrees. So we have an angle theta of 50 degrees. And m now is equal to 600 times 5.68 sine of 50 degrees. So the value of the moment m of 600 Newton about a point O is equal to 600 times 5.68 times sine of 50, so equals 2,610 Newton meter. So this is the moment M. So for your coursework number 2, you have to calculate the moment of a 90 Newton force about a point O for the condition of theta equals 15 degrees. And also, you need to determine the value of theta, which the moment about O is equal to 0. So that is your coursework number 2. So we have also what we called a couple. So the moment produced by two equal opposite and non-collinear forces. So the moment of a couple has the same value for all the moment centers. So if we have a vector approach, so M is equal to RA times the cross of F. So plus RB cross negative F. So we have uh, R cross F. So the couple M is a free vector. Then for equivalent couples, change of values of F and D. So the force in different directions but parallel plane. But the product of FD remains the same for equivalent couples. So for force couple system, so the replacement of a force by a force and a couple. So force F is replaced by a parallel force F and a counterclockwise couple FD. So we have example number 4. Replace the force by an equivalent system at point O and also reverse the problem by the replacement of a force and a couple by a single force. So we will only answer condition number 1. So we will replace the force by an equivalent system at point O. So the force couple system. So as you can see in this figure, so we have here a force of 400 Newton with a moment arm of 200 millimeter. So at an angle of 60 degrees. So to replace this one, we need to draw a force here which is equivalent also to 400 Newton and force here which is equivalent to 400 Newton. So since the force, the aim is to translate this force to this one, to this point O. So to replace this one, so we have a moment which is equal to 400 Newton multiplied by the 0.2 times sine of 60. So we have M is equal to we have 69.28. Then it is in a counterclockwise direction. So moment O. So therefore, to clear the figure, so we have point O and the moment MO, which is equivalent to 69.28. So this is 0.28. Then the unit is Newton meter, and a force F at O, so this is 400 Newton. So that is our equivalent force couple system for this example. So for resultants, this is the simplest force combination which can replace the original forces without changing the external effect on a rigid body. So resultant is equal to a force couple system. So to get the resultant, so we have for a 2D system, we have the resultant x is equal to the summation of forces along x, and the resultant y is equal to the summation of forces along y. And to get the resultant force R, so we have the square root of the summation fx squared plus the summation of fy squared. Then the angle is equal to arctan r sub y over r sub x. Then the summation of moments is equal to summation of forces times the perpendicular distance. So, for example, moment at O is equal to R times D, wherein R is our resultant force and D is the perpendicular distance. So for coursework number 3, you need to replace the three forces acting on the bent pipe by a single equivalent force R, then specify the distance x from point O to the point on the x-axis through which the line of action of R passes. Then for part B, we have the three-dimensional force systems. So the rectangular components of the vectors in 3D, if we have the vector F, so the corresponding rectangular components in 3D equals fxi plus fyj plus fzk, wherein our fx is equivalent to f times cosine of theta x, and our fy is equal to f times cosine of theta y, and our fz is equivalent to f times cosine of theta z, wherein our cosine theta x, cosine theta y, and cosine theta z are the direction cosines, and the magnitude of force F can be obtained by this formula. So rectangular components in a 3D. So if the coordinates of point A and B on the line of action are known, so we have vector F is equal to the magnitude of force F times the unit vector. So we have the formula. You can just follow the formula in order to get the rectangular components in 3D. So if the two angles, theta and phi, which orient the line of action of the force are known, so these are the formulas. So for coursework number 4, the cable exerts a tension of 2 kilonewton on a fixed bracket A. So write the vector expression for the tension T. So for coursework number 4, you need to write the vector expression of the tension T, which runs along line AB. So for example number 5, we are asked to find the projection of T along the line OA. So first, we need to determine the vector components or vector form of our T along line AB. So our T is equal to Txi plus Tyj plus Tz. Okay. Then it is equivalent to T times the zero minus 1.2 I plus 0.5 minus 0 J, then plus 0.4 minus 0.3 K, then divided by the square root of negative 1.2 squared plus 0.5 squared plus 0.1 squared. So equals to 2 kilonewton for the value of T times negative 1.2 I over 1.304 plus 0.5 J over 1.304 plus 0.1 K over 1.304. So our vector T is equal to negative 1.84 I plus 0.767 J plus 0.153 K. Then the unit is kilonewton. So let us remember this value. So let us write it here. Our T is equal to negative 1.84 I plus 0.767 J plus 0.153 K kilonewton. Then for our line OA, so let P be the representation of our line OA. Then P dot T, so the dot product of P and T is equivalent to PT cosine of theta. Then since we are looking for the projection of t along line OA, so we have t cosine of theta is equal to the dot product of the vectors p and t over p, and it is equal to the unit vector of p times t. So next, we need to find the vector equation for our p. So p is equal to 1.2i plus 0.3k. Then to get the projection, so we have t cosine of theta equals our p over p times t. So we have 1.2i plus 0.3k times our t is equal to negative 1.84 I plus 0.767 J plus 0.153 K, then divided by our P, which is the square root of 1.2 squared plus 0.3 squared. Then to simplify our T cosine of theta, which is the projection of T along line OA, is equal to negative 1.78 I plus 0.04 K kilo Newton. And that is our answer. So for moment and couple, so the moment of force F about the axis through point O is equal to the cross product of R and the force F. So evaluating the cross product, we have here the determinants. We have IJK, then RX, RY, RZ, and FX, FY, and FZ. So to give you an example, so in example number 6, we have a tension T of magnitude 10 kilonewton is applied to the cable attached to the top A of the rigid mast and secured to the ground B. So determine the moment mz of T about the z-axis passing through the base O. So if you will look at the figure, the force T is directed downward. So therefore, to get the vector notation of our tension, so we have T. So we have T is equal to the magnitude of the tension times the AB over, so it is equivalent to 10 kilonewton for our tension or our force T, then times AB is 12 I minus 15J plus 9K. Then divided by the square root of 12 squared plus negative 15 squared plus 9 squared. So where does this 12, negative 15, and 9 come from? So if you will look at the figure, so since the t is directed downward, so the x coordinate is positive, positive 12 towards the positive. So we have positive 12, and from A to B, the is negative 15 units. So down by 15 units. That's why it is negative. And the z coordinate is 9 units. So we have the expression 12i minus 15j plus 9k. So to simplify, we have our t is equal to 4 square root of 2i minus 5 square root of 2j plus 3 square root of 2k. Then the moment of t about point O, so we have the moment of t about point O is equal to the cross product of r OA, so times, so the our TAB. Then so MOT is equal to I, J, and K. So we have for ROA, we have the coordinates of 0, 15, and 0. Then we have for 4 square root of 2. Then for TY, we have 5 square root of 2. And for TZ, we have 3 square root of 2. So what we are looking for is the MZ. So MZ is equal to this one. So 0 times 5 square root of 2 minus 4 square root of 2 times 15. Then this is K. So our MZ is equal to negative 84.85 kilonewton meter. And that is our answer. And that's it. Thank you very much for listening. I hope you learned something, and kindly submit the courseworks accompanied in this video in our next meeting.